touch of an R3.
Department number 3. Department number 3.他相同的角色没有做这个事，他如果是他上
对，但是没关系。
没关系啊，他做第一两项，
比如第三场是保护的选。哦。这是小的给大家介绍。
Hello everyone, my name is stage3 from Andromeda, and today I'm going to report problem number 3 lato. And first is a problem statement. Attach a ball to each end of a string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the ball starts to oscillate, and oscillate with increasing amplitude. And the problem statement asks us to investigate the phenomenon. So in my further report, I will be mainly focused on number 1, why will the amplitude increase and then reach a maximum value? The second one is the relevant parameters that affect the results. Third is an observation. After doing some experiments, I found that there are 2 states of lato. The first one is the amplitude increasing state. As you can see from the video, the amplitude between 2 latos increases as they collide. And the second state is the stable state. As you can see from the video, the amplitude between 2 latos basically remain the same. Next is our theory. In our theory, first we will start from a force analysis to how to define collision, and then I will talk about what is our modeling, how do we do our modeling, and then I will explain why will the amplitude increase as what the problem statement says, and also why will it reach a stable state after a few seconds. First is force analysis. In force analysis, we put our observer on the pivot. The reason why we will do that is because we can make all the force that is applied on the lato really easy. We can ignore the unnecessary complex calculation. So after doing that, one lato is affected by 3 forces that will affect the motion. The first one is gravity, the second one is resistance, and the third one is imaginary force. The reason why we need that is because we put our observer on the pivot. It's a non-inertial coordinate. So we can get this formula here, and after we get it here, we kind of rearrange the formula and we can get a formula below. And the reason why we need to rearrange that is because we will use this formula to describe the further theory. Next, for the collision, the way how we define collision is when the angle between 2 strings is smaller or equal to the minimum angle that it can be. So we will define that as a collision. If it's greater than theta 0, then it is separate, so it's still moving. And for what kind of collision we are talking about, first we have to calculate the coefficient of restitution. After doing that, we get that RE will equal to 0.929, which is smaller than 1, so it means that our collision is a non-elastic collision, which means there's definitely energy loss during this phenomenon happen. Then it's our modeling. We combine force analysis and how to define collision and what kind of collision we are talking about into this form, and then we add Taylor series expansion because the theta that our lato can reach is not smaller than 5 degrees. So we can get this formula and we use this to run our modeling, and we can get the formula like this. So later on, if I use any theoretical data about frequency or period, I'm using this kind of graph and I can calculate the period between each gap. Okay. Next, I'm going to talk about why will the lato oscillate with an increasing amplitude. And first, we need to know what is a parametric oscillation. A parametric oscillation is a system of parameters varies with time, which will give additional force to the amplitude so that the amplitude will increase. So in order to use all the properties of this theory, we have to rewrite our formula. So the reason why we can say that this is a parametric oscillation is because we rewrite our formula into this part, as I just said in the force analysis part, and you can see this part as the gravity of the whole system is varying by time. So if we look at it in this way, then it will fit the parametric oscillation. So in order to fit all the properties, we rearrange our formula and we get this one. Okay, and after getting this one, now we're going to talk about why and under what circumstances will the amplitude increase. So now we have to use the mathematical formula. And this formula is going to talk about what I say, the amplitude increase. So we have to non-dimensionalize my formula into this part so I can use all the properties in this theory. So after doing that, we can get this formula, and then the A in this formula will be relevant to the natural frequency of the lato and the frequency that our pivot is moving. And Q will also be relevant to the natural frequency of the lato. And then, why is there 2 states of lato? And now we have to use the unstable concurrent. In this graph, we just talk about the A and Q in the formula. So The A and Q in this formula can be used in this graph. So if the value of A and the value of Q is inside the blue part of this graph, then it is called an unstable state. In the unstable state, the amplitude will give the system additional energy, so the amplitude will increase. That is what we can do on unstable state. So we just figure out the first question: why will the amplitude increase? And then it comes to the second question: why will it reach a stable state? The reason why it will reach a stable state is because normally if it's in an ideal situation and the A and the Q is the value of A and Q is inside the blue part, then the amplitude will increase with no limit. However, in reality, we have different kind of energy loss, such as air resistance and all sorts of energy loss. So there will be a point when our input energy is equal to output energy. Therefore, that's why we can get a stable state. And this is our modeling formula. You can see that in this part, I control our coefficient of restitution as 1. So there's basically zero energy loss here. So that you can see that the radius between the two levels can reach 360 degrees. However, if I change the coefficient of restitution to 0.5, then the maximum angle it can get is only 4 radius. So that can prove that what I'm saying is correct. If we don't have any energy loss, then the energy will increase unlimitedly. However, we have energy loss, so it's why we can get into a stable state. So next is about experimental setup. For our setup, we use our hand to control the lato, and then we have a hole on the platform so we can control the amplitude, and we listen to the metronome sound so we can control the frequency. And in our experiment, we changed the rope length by 18 and 23 and 28 centimeters and the pivot frequency. And we are going to observe T1 and T2. And about what is T1 and T2 here. As you can see, there are two parts of the graph. In the blue part is the amplitude increasing state that I just talked about in the observation part. So we identify the time period in the amplitude increasing part as T1. And we identify the time period in a stable state as T2. And now we can finally go to our data analysis. So for data analysis, first we change the pivot frequency. So as you can see from the graph, the blue dot represents the experimental data, and the red dot represents the theoretical value. And why is there a theoretical value instead of a theoretical line? It's because that what my model can get out is a time versus angle graph. I don't have the formula that can just tell me what is the frequency. So that's why there is a theoretical value instead of a theoretical one. So this is the comparison, and as you can see from the graph, that when the pivot frequency increase, the Laplace frequency will also increase, and this is in the amplitude increasing state. And then we're comparing the pivot frequency to the Laplace frequency in a stable state. So also, as you can see from the graph, that when the pivot frequency increase, the Laplace frequency will also increase. And if you compare this one with this one, you can know that the difference between theoretical and experimental data is bigger when it is in the amplitude increasing state. And I believe the reason that will cause this is because when it is still in the amplitude increasing state, it is really unstable. So it will also kind of affect what the hands move when it. So I think that is the reason that will cause the difference between theoretical and experimental data. And for why when the pivot frequency increase, the Laplace frequency will also increase. The reason for that is because, as I just said, the Laplace equation will fit the parametric oscillation, and this oscillation will also fit the flow phase theory. And this theory is going to talk about the differential equation with periodic coefficients. And the periodic coefficient over here is what I just said. Is the way how we arrange our formula, and then we get the formula for parametric oscillation. So because this part will periodically vary, so we can know that this will fit the flow phase theory. So in the flow phase theory, because what we use is the parametric oscillation. So when we use the parametric oscillation, the mu which is in the formula here will contain real number. So when the mu contains real number, there will going to be an integral ratio relationship between the pivot frequency and the system's frequency. So you can kind of represent it like this. So the system's frequency will have an integral ratio with the pivot frequency. So we can know that when the pivot frequency increase, the system's frequency will also increase. Next, we're going to talk about the rope length. So as you can see from the graph, the dipole frequency will decrease. And the reason for that is because, as I just said about the flow case theory, we can know that there are parametric oscillations, so mu contains a real number, so there's an integer relationship between the frequency of the pivot and the frequency of the system. So we know that, so we can get this formula here. When we know that the frequency of our pivot was k times the frequency of the natural frequency, then we can, and we assume that, okay, so then the frequency of the system will be this, will equal to this of the frequency of the hand. So we will know that when the rope length increase, and then the natural frequency will decrease. So, and also because of the pivot frequency will stay the same. So when k increase, n will increase. So the system frequency will decrease. And that is why when the rope length increase, the system's frequency will decrease. And that is discussion. First, I observed that there is a periodic pattern in the standing wave. And I think the reason why that will happen is because there is phase difference between hand's frequency and the ball's frequency. So sometimes it will input energy and sometimes it will output energy. So I think that is the reason why there will be a wave here. And then, how will lateral collide above the pivot? Because normally that's how we play it. After I've done some research, I noticed that you cannot. There's basically not really a big chance that you can make the lateral collide above the pivot with just the same amplitude and the same frequency. So if you want the lateral to bump up on the top, then you have to give it a solid extra amplitude so that it will have a solid extra energy, so that it will get up to collide. And so that's all for my presentation. Thank you.
Okay, so first, thank you for your report. I have a very short question for you. So, first, in your theory, did you assume the string is always straight?
In my theory, yes.
Okay, thank you. Now, in terms of page 4, so you mentioned that in your experiment, the height stops changing after a certain value. Is that correct?
Yes.
So you try doing maybe changing other parameters to see if the height will increase if you change other parameters?
I believe so.
Okay, so did you do those experiments?
Yeah, no, but it's not. I didn't put it here.
Okay, thank you. So in your theory, did you only consider the 2D motion on the balls?
Yes.
Okay, can you turn to page 7? Like you meant, E is the coefficient of restitution, am I correct?
Yes.
And so how did you measure that?
Because we can get the velocity before the collision and after the collision, and after the collision you can get the number.
Okay, so what's the were you still oscillating the pivot when you were measuring the coefficient of restitution?
No, I'm not moving the pivot.
Okay, I think we'll talk about this later. Okay, so can you turn to page 13? So you mentioned that you control your lateral level by hand. So how did you control the frequency?
I put on headphones and I will listen to the metronome so we can control the frequency.
Okay, so did you try to measure your hand's frequency to make sure it is the same as the hand's frequency?
Yeah.
Okay, so does your hand oscillate at the same amplitude?
Yes, because I said I have to dig a hole in the board, so I make sure that my hand is moving the same amplitude.
Okay, and that's all my questions.
Thank you.
And today I'm going to be opposing problem number 3, lateral. Okay, so this is the problem statement. First, you attach a ball to each of the strings and connect the center to a pivot. So we have to oscillate the pivot along the vertical direction. And the balls will start to collide and oscillate with increasing amplitude. And we have to investigate this phenomenon. So first, for the theory of the reporter, they considered an inelastic collision, and they analyzed the different forces acting on the balls, which include the tension from the string, the gravity, and also considered an inertial frame for this system. And they also managed to calculate the coefficient of restitution, and also managed to consider the damping for this, and for example, the air resistance. And in their theory, they also managed to talk about the two states of the lateral and explain why the amplitude no longer increases. Next, as for the experiment, first up, so they used a lateral, and then they used their hands to control the lateral, and they used a metronome to control the frequency of the head, which we'll also discuss later. Okay, so the main parameters were the length of the rope and the frequency of the pivot, and when the frequency of the pivot increased, they found that the lateral frequency also increased. And so when the rope length increased, they also found that the lateral frequency increased. Okay, so onto the strength and suggestions of the reporter. First, I would like to commend the reporter for trying to control the experimental setup. And although they did use their hands to control the experiment, they did try to at least control the frequency and the amplitude through using a metronome, for example, which I think is a very good attempt. Next, they also managed to have a complete explanation about the motion of the lateral, and for example, they also talked about the different phases of the motion of the lateral. They also gave some qualitative explanations, and they also managed to derive a complete quantitative theory using their force analysis and some mathematics. And they also ran some simulations based on their theory, and they also managed to compare their theory with their experimental data, which is very commendable. However, onto the suggestions. First of all, I think there could be more explanations as to how the energy transfer goes on, because I think this is quite a complicated system. And also, I think there was a lack of discussion about when the amplitude increases. So in their experiment, they found that the amplitude stops increasing after reaching a certain height. However, the problem statement mentions that when you oscillate it, the amplitude will keep increasing. So perhaps there were some partial unfulfillment of the problem statement in this respect. And as for the setup, while they did manage to try to control how they shook their head, for example, they didn't mention how they managed to control the horizontal displacement of their head, which I think will also affect the lateral performance. And also, as for the damping, they also did consider that in their theory. However, when they did try to measure the coefficient of restitution, they could add more explanation about how they managed to measure the coefficient of restitution, and also the value they measured seemed to be very high, which I think we will discuss later. And finally, they only discussed the lateral in a 2D scenario, which we might also discuss later, and that's all. Okay, so next I would like to invite the reporter. Okay, first of all, I think we'll talk about why the lateral amplitude increases, and why in your experiments they stop increasing after a certain amplitude.
Okay, of course. First, we need to start from, I just say, do you understand the part I say that, because you can see this part as the gravity varies through time, so it can be seen as a parametric oscillation.
Okay, yes.
Yes, okay. So if this stands, then if this is a parametric oscillation, then it can fit the Matthew formula. And if you want to use Matthew formula, you have to non-dimensionalize your original formula into that form. And after doing that, yeah.
Thank you very much about the very detailed explanation. And so what I'm actually more curious about is why the amplitude actually stops increasing. So you mentioned a stable state effect, right?
Yes.
Okay, so I think that the problem statement asks us to investigate when the level amplitude actually increases. So, for example, what do you think will cause the amplitude to increase? For example, do you think it's mainly the frequency of the pivots?
Okay, so I think the main reason that why the amplitude will increase is because the value of the natural frequency of the lato and the frequency of our hand is in a certain value, which is in the blue part of the unstable tone graph. So if it's in that situation, then the amplitude will increase.
Okay, so perhaps in your presentation you could mention the relationship between your hand frequency and the natural frequency of the lato, and also talk
Yeah, I
about
have talked about the pivot's frequency, and that will be my hand's frequency.
yes, but perhaps you could also talk about the boundaries for this situation. And also, you mentioned the natural frequency of the lato. So what do you mean by its natural frequency?
When I say it's natural frequency, I mean gravity divided by the length of the rope and then curved.
Okay, so I think that's quite similar to the interval for a simple pendulum. So what you're thinking is that when you use the lato as a simple pendulum, the interval at which the pendulum is swinging is also the natural frequency of the lato. Is that correct?
Wait, so your question is that is the lato frequency equal to the natural frequency? Is that what you're
So am I correct in what you're saying is that the natural frequency of the lato is equal to the frequency that would be observed if you were to convert the lato into a...
No, that's not what I'm saying. What I'm saying is that there is a relationship, there is an integral ratio relationship between the pivot's frequency and the natural frequency.
I think in well, you mentioned that the frequency is like this, right? Okay, I'm sorry, my mistake. So you think it's related to how the lato, for example, if this is the length of your lato, it will be related to how it swings when it is a simple pendulum, is that correct?
Oh, so you mean it's not exercise instead of simple pendulum?
Okay, I think.
If it's what you're saying, then yes, that's true.
Okay, thank you. That makes you move to why your lateral amplitude is increasing. So you mentioned stable regime. So you did not try to change some parameters to further increase the amplitude when it reaches the maximum height.
You mean I should change a lot of parameters so that after it reaches stable that it can keep increasing?
Yes, because I think that's what the problem statement mentioned, and it's also quite an important part.
I think what the problem statement is trying to say that I should observe the part where the lateral amplitude will increase. And I think I have observed why it will increase, and I will observe that okay, there will be a stable state. So the explanation of the stable state is just telling that there is a stable state, why they will happen.
I think we'll agree to disagree on our interpretation of the problem statement. However, when it reaches a stable state, perhaps because the angle of this angle is rather large, so perhaps the actual frequency will change. Do you agree?
So what you said when you reach a stable state, the frequency will change.
So perhaps because the frequency we usually use to calculate is for a small angle. Do you agree?
Yes.
Okay, so perhaps when it reaches the maximum height, it's no longer a small angle, and so the frequency of, for example, it will kind of change. Do you agree?
Yes, twice please.
Okay, so I think that perhaps when it reaches this stable state, perhaps you could try to change the frequency of the pivot during the stable region, and perhaps that will cause the oscillation of the level to increase again. So I think that perhaps you could try to change the frequency during your experiment in the future and see if that will actually change it. Yeah. Next, you mentioned that you consider the
how I measured is that I put two balls like in the height, so we hold the ball, and then you ask me if the ball is moving. No, it's not moving. It is stable. So we release the ball, so the ball go down here, and it will go here with like V1, and then go here with V2.
Yes. So you mentioned that the value you calculated was something like 0.93, right?
Yeah.
And I think that's actually quite high for it. And it feels like it's actually. So what's the material of your balls?
I believe it's plastic.
Is it bouncy or is it just?
No, it's hard. It's like kind of rigid, but it's just that's.
Okay.
Yeah, that is the material of my body.
Okay, so I think that's right. That is the coefficient of substitution as you finish to measure was quite high. So like for example, it's kind of like if you drop this ball on another ball, when it rebounds, it will go almost to 90% of the original height. And so I think it's actually quite high for like kind of hard plastic you're using. It almost feel like it's some kind of bouncy ball. What do you agree?
I'm not sure if whether it will bounce like this, but according to my calculation, that's the coefficient, yeah.
And perhaps you could also explain that in the future. Next, and also let me talk about some of your experimental results.
Which part of it?
Okay, we'll go first to the length of the code.
Yeah.
So you mentioned that the lattice frequency is related to the natural frequency, am I correct?
I mentioned that the lattice frequency is related to the lattice frequency.
Okay, and so did you also does the amplitude increase in all these frequencies? Or did you just measure the level frequency?
What do you mean the amplitude? The maximum amplitude?
Yeah, so like during this part is like oscillation of the level continuing to increase.
The amplitude will increase.
Okay, never mind. So what you're saying is that
Yeah, but what I'm saying is that you can see from the graph that when the length of the rope increase, the frequency will decrease, and my explanation is here. So,
okay, I think that enough for this part. And also about your, I want to go back to your setup. Yeah, so in the level, you mentioned there's this kind of like wall, right? So is the level like actually touching the?
no.
Okay, so is it ever possible that your level will not try a straight down faster? They only.
Then we will count the experiment.
Okay, thank you. What about the horizontal displacement of your hand? So did you? Okay, thank you.
Okay, this question is about. So the opponent can normalize.
Okay, so my conclusion of my discussion with the reporter, first of all, we discussed when the amplitude of the rental level increases. And the reporter mentioned a stable state, and I think that they could also talk about its relation with the pivot frequency a bit better. And also, in the reporter's experiment, the rental level amplitude manages to stop increasing after a certain range. So perhaps, in my opinion, it is a bit different from what the problem statement is saying, as the problem statement says that the rental level will oscillate with increasing amplitude. So I suggested that the reporter perhaps change the frequency of the pivot during when the level is still oscillating, as the larger angle may cause the frequency of the level to change, and perhaps changing the frequency of the pivot will allow the amplitude to continue to increase. We also talk about how they measure the coefficient of restitution, and that's all. Thank you.
You use stage for
temperatures, like when they reach a certain amplitude, then it will be equal. So they won't increase anymore. Okay. And what is the?
When is the temperature will increase?
Yes.
Something that frequency of the pivot only correspond to the representation of the natural frequency. And I think that also the amplitude of the pivot is important, as if the amplitude is too small, perhaps the amplitude of the lateral will increase.
Okay. And do you think there are some of them at the methanol because Schumann's reaction might be less than the? Maybe there will be some errors. I won't be disagree, but that's why we use model. We have the theoretical one, and you can see that my theoretical trend is really like the same with my data set. So I don't think it's that big of an accurate. Do you think that's will affect the reaction of humans? The natural frequency?
Yes, so I suggested that the reporter also perhaps track how their hand is moving to account for this inaccuracy.
Okay, and you mentioned that there are two states. What causes that, and what's the difference of two? The two states is that the first one is when the amplitude is increasing. The second one is when it's stable. And the reason that when it's increasing is because the value of A and the value of Q is in the blue part of the time graph. So I think that is why it's increasing. Okay, and you know how if the state will get to another state? What's your opinion?
So in the current experiments, they seem to stop at a stable state. So perhaps changing the frequency will cause the lateral to change into another state and continue to increase their amplitude.
And what do you think of natural frequency? Can it calculate? Or?
Yes, like the reporter mentioned that the definition of natural frequency, and I think that it will be related to how the lateral will perhaps swing when it is like a pendulum.
Okay, and what do you think the difference of experimental and the theory? I think because we use our hands, so I should just say it's definitely some error, but it's not that big, so I don't think it is that important. Okay.
OK，看一下reviewer email。And she can also do the experiment that can control the force
he listened lots of the cons in that report test, and but I have some suggestions for him. I think he can ask his question more clearly and to let the reporters understand her question much faster. And we have discussion that the opponents asked the reporter how the handshaking impacts the frequency. And the reporter said the force are used to shake. And I think handshake will affect. And the opponents also asked what the material of the reporter's ball. She believes that it was made by plastic. And thank you. Okay, I'm the reporter from Andromeda, and here's my concluding remark for problem number 3, Lato. And first, we discussed about the measurement of the coefficient of restitution, and he said that he normally thinks the measurement is correct, but I don't think so, because when I'm measuring, I have to control the pivot that is stay at the same place, and I just drop the two balls, so they'll have collision at the down part, and then we calculate the velocity before it and after it. So I think it's accurate. And then we also talk about what caused the amplitude of the lasso to increase. I have talked about like 3 times in my presentation, and it's because the value of my hand's frequency and the value of the lasso's natural frequency is in a certain range, which is in the blue part of the unstable time graph. So that is why the amplitude will increase. And then we also talk about the effect of the way to climb the lasso by hand. And I also know that maybe it's not that accurate, but that's why I have used modeling to prove that actually my experimental data is it will fit the modeling data. So I don't think it's going to be a difference, but not that much of a difference. So I think that is a really important part in my presentation. And that is my conclusion. So in the observation part, we talk about 2 states of plateau. The first one is amplitude increasing state, and the other one is the stable state. And we use force analysis and collision to run our modeling to get our theoretical value. And then the way we use a parametric oscillation and the mathematical formula to describe why will the amplitude increase and then reach a stable state is because the energy will eventually get into a balance point. And then we use the focus theory to prove that why when the amplitude increase, the frequency will also increase. So that is all for my presentation. Thank you.
Okay, now the question. Okay.
So maybe one of the important points using the hand is precise enough or not, right? So could you all of you give me for example, the overall value estimate? If you have 10% error in frequency or anything here, then what will it cause the final entry? How many percent? Give me an overall value estimate for that.
So you mean that the enhanced amplitude?
Yes, definitely your frequency up to you. You have 10% difference.
Okay.
And then what will be the difference in the final amplitude?
I think it will be less than 20%.
And please justify.
I think the reason is because I think it's because that the system of the sorry, I changed my answer. I think it was the same. Yeah.
All of it?
Yeah.
Maybe less than 1%?
No, I think it will be the same percentage that the frequency of the hand is
Okay.
difference.
Okay. So, equation?
oscillate pivot is also very important because if the phase
Give me a number.
I think perhaps less than 10% is the maximum.
Okay, and just
I think it will also depend on the person's like feeling for the frequency of the metronome. So it will depend by the person.
I think it will bigger than 10%. It's frequency wise is
no, even if it can have a 10% difference, how about the output? Output is empty. It can have 10% uncertainty. The uncertainty of everything is 10%, 1%, 0.1%, or 100%.
how?
I mean, yeah, you have to answer. Because all of you think this is a very important issue, right? How important is it?
Try to yourself from the experience.
Okay.
Any more questions? Oh,
All of you, what's the physical mechanism to make this temperature increase? Why the temperature? In other words, why the temperature keep increasing?
So the head will provide a driven force, and like the driven force oscillation will cause the temperature to actually increase.
The answer is that because at the first part, the input energy is bigger than the output energy. So I think that is the reason why the amplitude will increase. And when there is a stable state, it means that the input energy is equal to output energy. So I think that's why the amplitude will increase.
What is the input energy and output energy?
It's because when your head is moving, and it will give the whole system an energy. Is an external force, so it will give the whole system energy. So that is when the input energy, and I think the output energy is when like air resistance and I think it's about air resistance.
I think because the head is giving all the force, so its energy might be more and its amplitude will bigger.
okay, now we come to the stage 3. Okay. Now the points for the recording. 86777. And now the points for the opponent. 76767. And now the point for the reviewer. 65655. Okay, 6 the king for the bookend.
请今天所有的 reporter 在这
着你的电脑过来我们这边，我们需要 copy 你的档案，然后还有带着你们下一场需要选的